Hi, good morning everyone. I am myself K. Narsimurthy. Presently, I am working as an assistant professor in Government First Aid Women's College, Tumkur. I am going to present a video in the subject physics, and this is my 53rd video for the second semester students of Tumkur University. I have been presented 52 videos for the second semester students. Almost 80% of the syllabus I have been completed in my 52 last videos. Now the 3 units which I completed in 45 videos and 45 sessions, each session is I have done one video in each session. So 45 sessions, 45 videos has been done, and 75% of syllabus is covered in 45 videos. Now after 45 videos, in the last unit I have done a very small chapter in 5 videos, and that was the transient current. I discussed the transient current along with the numericals in 5 videos from 45 to 50. Now from 51 I took up a new chapter. It's a very small chapter, in fact, that was the alternating current. I have defined you some of the basic things, some of the basic ideas of these alternating current, and how will be the average value of an AC in one half cycle and how it will be for one full cycle, and very few fundamental things regarding this alternating current. After that, I took up a very important derivation of LCR circuit. It's a series LCR circuit with an AC source using J operator method. I have used a J operator method to solve this LCR circuit of an AC, and I derived an equation for current. After deriving an equation for current in a series LCR AC circuit, I have discussed 3 very important cases which come across series LCR circuit, where the impedance, inductive reactance is sometimes greater than capacitive reactance, and sometimes capacitive reactance is greater than inductive reactance, and sometimes both are equal. And these are 3 important cases which I discussed, and I looked for the phase between the current and voltage in 3 different cases. I looked for the which one is leading and which one is lagging, and what is the value of phi, whether it is positive or negative. Okay, these are some of the very glimpse of the last videos which I have done. Right, after doing a very important derivation of series LCR circuit in AC using J operator method, now I am going to look for very few small things. So here I am looking for series resonance circuit. Now the term resonance itself tells you that something is matching, some frequencies are matching, and what actually those frequencies which are matching here in this series circuit. Now you know what is series LCR circuit is. Means it's an inductor, capacitor, resistor which are connected to an AC source. This will make a series LCR circuit. In this series LCR circuit, if the natural frequency of the series LCR circuit is equal to the applied frequency, then the current will be maximum. Now what mean by natural frequency? An LCR circuit will have its own natural frequency. If that frequency matches with the applied frequency, means the frequency which you are giving with an AC source, you are applying a frequency with a function generator. You are giving some 100 Hz, 200 Hz, 300 Hz frequency with a function generator. Okay, if that frequency, the applied frequency which I am giving, is equal to the natural frequency of the series LCR circuit, then the current in the circuit becomes maximum, and that particular frequency which I am applying is called the resonant frequency. Resonant frequency is that particular frequency at which the natural frequency and the applied frequency matches and the current becomes maximum. Okay, and this circuit is called resonant circuit. Why it is called resonant? Because the frequencies are matching. The applied frequency is matching with the natural frequency of the series LCR circuit. If there is a matching frequency, we are calling it as a resonant circuit. And it is also called acceptor circuit because of the same reason. It is called acceptor circuit because when the frequencies are matching, the current becomes maximum. The current becomes maximum in the series LCR circuit at resonant frequency. That is why this circuit is called acceptor circuit. Now, we know the equation for impedance, and I have derived an equation for impedance in the last class. Z equals R square plus omega L minus 1 by omega C whole square. Omega L is XL, which is called inductive reactance. 1 by omega C is XC, which is called capacitive reactance. Z is what the impedance. Now how do I define an impedance? Impedance is the opposition offered to the flow of an AC current, flow of an alternating current by these circuit elements, by these three circuit elements like resistor, inductor and capacitor. And equation for Z is root of R square plus XL minus XC whole square. You can take XL as omega L and XC as 1 by omega C. Alright, this is the equation for impedance we know and we have derived in the previous video. Now, at resonance what happens? This inductive reactance is equal to the capacitive reactance. XL is equal to XC. If that is the case, then Z is equal to R. It is only a resistor which contributing for the impedance. Okay, if Z is equal to R, that is the minimum value of impedance. The impedance is minimum means current will be maximum. At resonance, you can expect a maximum current because the impedance is low. Impedance is only the resistance. It's because no contribution from inductive or capacitive reactance. Look at the graph. Look at the graph of current versus frequency which I have drawn for a series LCR circuit. Suppose if frequency of applied voltage increases, the frequency which you are giving to the circuit of applied voltage, if you increase the frequency with the function generator, current increases. That was shown in the graph. Frequency increases, current increases in the circuit, and at particular frequency the current in the circuit becomes maximum, and that particular frequency is called resonant frequency. Resonant frequency is that particular applied frequency for which current in the circuit is maximum. If the frequency is further increased, then current in the circuit will decreases. Okay, current increases, attains maximum and then decreases with increase in the frequency. And the resonant frequency is that particular frequency when the current attains the maximum value. Why it is happening like this? Why is current increasing and attaining maximum value and then decreases? Why it is so in the series LCR circuit? I will analyze this. Okay. Yeah. Suppose if F is small, the applied frequency which I am giving is very small. Now if F is small, you know 1 by omega C is greater than omega L. 1 by omega C, its capacitive reactance, is greater than the omega L, which is inductive reactance. So it's because F is small. F is small, 1 by omega C will be greater than omega L. Upper one is 1 by omega C, lower one is omega L. The difference omega L minus 1 by omega C is negative. If this is negative and we are doing a square and impedance is greater, go back and look at the impedance equation. Omega L minus 1 by omega C, the gap is high. The gap is high for low frequency. So therefore if gap is high means squaring that will be more and impedance will be more. Now impedance will be more. Current is very small for lower frequencies. Then if frequency is increased, what actually happens is omega L, which is a very small value, will increase, and 1 by omega C, which is having higher value, will decrease. So omega L increase, 1 by omega C will decrease. So what about the gap between this 1 by omega C and omega L? That gap becomes very small. omega L minus 1 by omega C becomes very small. If this gap becomes very small, the second term in the impedance becomes small because the gap is small. So if second term is small, obviously Z is small. Impedance of the circuit will become small. Therefore, the current increases. And at particular frequency, this XL is equal to XC. Both are same. If that is the case, then the impedance is only the resistance. Then the current is maximum. Okay. Then after that, what happens? 1 by omega C still goes below. Omega L becomes increases. Okay. If you further increase the frequency, again the gap becomes bigger. Gap becomes larger. The gap becomes larger and larger. If gap becomes larger and larger, impedance of the circuit becomes larger and larger. If impedance is greater, means the current will decrease. So after the resonant frequency, the current will start decrease again. Okay, that was I satisfactorily explained with this kind of analysis. Okay, right. That is why in a series LCR circuit, current increases, and then after resonant frequency, current decreases. Right. If the value of resistance is high, the more broader is the curve. If the resistance is low, the sharpness will increase. The curve sharpness will increase if resistance is low. If resistance of the circuit is high, more broader and flatter is the curve. Now, sharpness is a factor which is a quantity we are going to define. It's a measure of quality factor. Now, sharpness of a curve is a rate of decrease of peak current at the resonance on either side of the peak value, on either side of the resonance. It is sharpness of the curve is defined as rate of decrease of current. Okay, rate of decrease of peak current on either side of the resonance at the peak value. So if the rate of decrease is more, sharpness is more. If rate of decrease is small, means it's a more flatter area, okay, sharpness is small. If it is more flatter, sharpness is less. If this is more sharp, sharpness is more. And that is decided by a resistance in the circuit. If resistance is more broader will be the circuit. Resistance is less, more sharper will be the circuit. So sharpness of the resonance is a measure of a quality factor. I am going to define in a next slide what actually this quality factor is. Right, we have a parallel resonance circuit. Resonance will also happens in the parallel circuit. So what is actually the resonance here? When again a natural frequency of a parallel LCR circuit is equal to the applied frequency, the current becomes minimum. This time the current becomes minimum, and that particular frequency is called resonant frequency, and this circuit is called resonant circuit, and this is also called rejector circuit. It is rejector circuit because at that particular frequency, at the where the applied frequency matches with the natural frequency, the current in the circuit becomes minimum. That is why it is called a rejector circuit. In the exams, you have this concept question category. That means the last category, where in the concept question category you can expect these kind of questions. They can ask why the parallel resonance circuit is called rejector circuit. Why it is? Because the natural frequency is equal to the applied frequency, then the current becomes minimum at that particular frequency. Therefore, this circuit is called the rejector circuit. Right. So we have a circuit like this. Inductor and the resistor are connected in parallel, and this system is connected in series with an AC source. Okay. Right. If I look for the resonance curve here, the curve will be exactly opposite to that of what I have seen in the series case. In the series case, it increases and decreases, but whereas in the parallel case, it decreases first and then increases. Okay, This is the nature of the curve I can expect in a parallel resonance circuit. Now here I can say that at XL is equal to XC at resonance when inductive reactance is equal to the capacitive reactance. Z is infinite. Z is having a very large value. When Z is having a very large value, the current becomes minimum. So that is why the current becomes minimum in this parallel LCR circuit. Now if look at the diagram of current, look at the figure of current versus frequency. Suppose if frequency of the applied voltage increases, if you go on increasing the frequency using the function generator like 100 Hz, 200 Hz, 300 Hz, 400 Hz, like this, if you go on increasing the frequency of the applied voltage, the current in the circuit will decrease. The current in the circuit will decrease as you increase the frequency of the applied voltage. And at particular frequency, the current in the circuit becomes minimum. It attains a minimum value. Okay, such frequency is called resonant frequency. If the frequency of the applied voltage is further increased, if you further increase the applied voltage after getting the resonant frequency, then the current in the circuit increases. Okay, the current in the circuit increases. This is the nature of curve in the case of parallel resonance circuit. So FR, where you get a dip, and that particular frequency is the resonant frequency. I have drawn a vertical line at the dip and I am looking at the corresponding X value, corresponding frequency at that particular dip, and that corresponding frequency is the resonant frequency. Right. Next, we shall define what is actually the bandwidth is. Now, it is a band of frequency which lies between the 2 points A and B, which lies between the 2 points A and B on either side of the maximum frequency. If that is the maximum frequency, we are looking on either side of the maximum frequency. We are looking at the 2 point on either side of the maximum frequency, where the response curve, where the impedance drops to 0.707 of its maximum value, 0.0707 of its peak value. Okay, look at the peak value. Peak value is I naught. So calculate I naught divided by root 2. I naught by root 2 will be I naught times 0.0707. So for that value, you draw an horizontal line where it touches the curve, where it touches our resonance curve at 2 points A and B. Draw the vertical lines from A and B and find out the corresponding frequency at the corresponding to the point A and B. And those frequencies, let us call it as F1 and F2. F1 is the frequency corresponding to the point A and F2 is the frequency corresponding to the point B. If I take F2 minus F1, that is the bandwidth of this curve. So I will repeat this bandwidth definition once again. Bandwidth is the band of frequency which lies on either side of the 2 points A and B, either side of the maximum of the frequency response curve, where this impedance drops to 0.0707 of its peak value, or you can say where the current drops from its maximum value to 0.707 of its peak value. Okay, that is correct actually. Rather than saying it is impedance drops, you can say it's a current drops from maximum to 0.707 of its peak value. Please make it correct. It is not an impedance, it is a current. Okay, current drops to 0.70 times of its peak value. It is I naught by root 2. And these points which I have mentioned, A and B, are known as half power points. A and B are the half power points, and F2 minus F1, the frequencies corresponding to A and B, the difference F2 minus F1 is called the bandwidth. Okay, right. So I have told you the sharpness of the resonance curve. So it was decided by the resistance in the circuit. If resistance is high, then the more broader is the curve. If resistance is low, more sharper is the curve. Yeah. Now we are at the last topic, which is the quality factor. I have told you that the quality factor is what decides the sharpness of resonance. The quality factor is defined as the ratio of potential difference across the inductor to the potential difference across the resistor. It is the ratio of two potential difference. What will be the unit of this? So it is VL divided by VR. Both are potential. You don't have any unit for quality factor. So VL divided by VR. Now if I substitute from the Ohm's law, if I substitute that, VL is I into XL, where XL is the inductive reactance. So VR, which is in the denominator, it is I into R. Again, it's from the Ohm's law. I get cancelled. You are left with XL divided by R. So quality factor Q is equal to 2 pi FL divided by R. Okay. So this is what the equation for the quality factor. Quality factor can also be defined as it is F naught divided by bandwidth. Quality factor is F naught, or in some books they are called it as FR. FR or F naught, both are the resonant frequency symbol. You can use anything for representing the resonant frequency. So FR divided by bandwidth is called the quality factor. So it is inversely proportional to the bandwidth. If bandwidth is more, the quality factor is less. If bandwidth is less, the quality factor is more. Okay, right? You can analyze this with the help of this kind of diagram. Okay, if this is the curve, if more sharper is the curve, because of less resistance, the curve is more sharper. If this is more sharper, then you can expect a less bandwidth. Bandwidth will be less. Bandwidth will be less means the quality factor is high. Okay, so quality factor is what decides the sharpness of the curve. If quality factor is more, sharpness of the curve will be more, and that is decided by the resistance in the circuit. Your bandwidth, your sharpness of the curve will be decided by the value of resistance in the circuit. If resistance is low, sharpness of the curve will be more and bandwidth is less. Therefore, the quality factor will be high. Suppose if resistance is high, resistance in the circuit is high, then the sharpness of curve will be less, means more broader will be the curve. More broader will be the curve. If it is more broader, bandwidth will be high. Bandwidth of this broader curve will be high. If bandwidth is high, therefore the quality factor, which is inversely proportional to the bandwidth, will be low. So quality factor will be low. Sharpness will be low. So sharpness is ultimately decided by the quality factor. If sharpness is low, quality factor is low. If sharpness is high, quality factor is high. And again, that quality factor is decided by the value of the resistance in the circuit. If resistance is low, sharpness is more, quality factor is more. If the resistance is high, sharpness is less and quality factor is also less. So everything is interlinked. So in bandwidth, quality factor and the resistance of the circuit, and these are all interlinked, and finally they all decides the sharpness of the curve. Okay, right. But if you increase or decrease the resistance, whether will that change the resonant frequency? No, I'll say no. Now if you increase or decrease the resistance in the circuit, in a series LCR circuit, that will not decide the resonant frequency, because the formula for resonant frequency, I suppose I have derived, I feel. No, I have not derived an equation for resonant frequency, which is a very simple thing. when XL is equal to XC, XL is omega L and that is equal to 1 by omega C. If the omega L is equal to 1 by omega C, omega L is 2 pi FL and 1 by omega C is 1 by 2 pi FC. Okay, so F you crash multiply, it becomes F square, and 2 pi you take here, it is 2 pi whole square, and 1 by LC. If you want F is equal to 1 over 2 pi into root LC. So resonant frequency equation will be F is equal to 1 over 2 pi into root LC. That I can derive using this condition, XL is equal to XC. Okay, so very simple thing. So FR is 1 over 2 pi root LC. There is no role of resistance here. Resistance will not decides the resonant frequency. If you increase or decrease the resistance, it is only the sharpness of the curve which varies, not the resonant frequency. So resonant frequency is decided by the value of inductor and the capacitor in the circuit, not the value of the resistance. I have left here this quality factor. It is 2 pi FL divided by R. It is the ratio of inductive reactance to the ohmic resistance. This way also we can define a quality factor. Ratio of inductive reactance to its ohmic resistance, or it is the ratio of potential difference across inductor to the potential difference across the resistor. So finally, quality factor is a measure of sharpness of the curve, and that sharpness was decided by the value of resistance, and the resonant frequency FR, which is equal to 1 over 2 pi into root LC, is what decided by the value of the inductor and the capacitor in the series LCR circuit, and in any circuit for that matter, either it is series LCR or in the case of parallel LCR, the resonant frequency is decided by the value of inductor and the capacitor. So these are some of the books which I referred for this series resonance and the parallel resonance curve. You go through it, you will understand things better. Thank you.